Is it on? Is it on?
You want me to do that?
Okay, right. Yeah. I think we have to many times.
So when are you going to start recording?
I've started recording, but they're showing other slides and I don't see.
Previous.
They could share the screen. You know what I'm saying?
Okay. Is this working? Yes.
Yeah.
Good evening, all you beautiful people. So I am Lalita Kamampati, and on behalf of ASEI, I would like to welcome all of you, express my gratitude for giving us the privilege of meeting all of you and to enhance the climate of ASEI's first in-person session of this year. So climate, that's something which impacts all of us in more ways than one. So we are lucky to have Professor Janice Means over here with us to speak about the topic, climate change, myths and realities. And I also would like to thank ESD for, going out of their way to support us all the way, providing us the venue, doing, ensuring that all the logistics are just right for us. So thank you so much. For those of you who are not familiar with ASEI, ASEI is American Society of Engineers of Indian origin. And so I just will show you the slides. So ASEI provides a platform for engineers and technologists to network, to exchange their thoughts about technology, and also encourage the youth to take up, engineering, technology, go into those fields. So we basically have 5 platforms, which ASEI caters to 5 platforms. One is pillars, really. Yeah, pillars. So it's one is Mentor Connect, one is University Connect, then is Corporate Connect. Then we have the Youth Technology Exposition. And last but not the least is networking, which we an event like today is what networking is all about, where we have a speaker and we talking about a topic which interests all of us, and we get an opportunity to connect with each other. So for any event to be successful, we need to have a really strong team that works behind it. And so this is the board so we have 2 levels, which we have the national, the ASEI national, and then we have the chapters. So this is the Michigan chapter, and this is the board for the Michigan chapter. So we have right now, whoever is there from the Michigan board. So I'll just call out the name. So whoever is over here, if you can just raise your hand or stand up. So there's okay. Then we have the Vice President, Ravi Majmudar. He's not here. Rakesh Saini is here. Yes, he's our treasurer. Jhansi Nala could not be here, so she's our secretary. Anjali Kotha is, she is located in Cleveland, so it's difficult for her to commute. She mostly joins our online, our virtual events. Then we have Ritu. Ritu's back there. And Ritu manages our University Connect. Vatsala Upadhyay. Kush could not be here. Ravi Ramamurthy. Yes, yeah. Anjali Tiwari. Raise your hand. Yeah, Ankur Singh was caught up at work. Shiva. Yes. Sridhar. And we have the advisors who are our veterans, really, who are the base for everything that's happening. So Muthu supported us all through the event. He was the one who connected the speaker with ESD, but he could not be here. He's in Colorado, but his wife is here to represent him. Jwalan. Yeah, Viji. Yeah. And Jwalan could not be here. Santosh Tiwari. Ram. Hey, Ram. Rakesh Patel couldn't be here, and Well also couldn't be here. But yes, this is our team for Michigan. And this is our national team. And we do have people from our national team here as well. We have Vatsala, who is the vice president of the national team. And then we have Ashwini. Yes. And that's it, right?
Yeah, but we have a large presence in the national team.
Yeah, from Michigan, we have a large presence. Like Michigan is very well represented in the national team.
But we have Muthu, who's the treasurer.
And you, Muthu, Ashwini, Jwalant, Rakesh. Yeah. 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 Yeah, Ashwini. And so these are some pictures from the events that happened. So, so we have, like I mentioned, we have the online, the virtual events, as well as the in-person. So every quarter, we intend to have at least one in-person event. And every month, we kind of have some activity, like it could be a virtual event, or it could be like we collaborated with, in March, we collaborated with IVA and the other organizations to for a celebration of International Women's Day. So, so these are some of the pictures from, and then we also do have mini summits. So these are pictures from the mini summit. And this is from the International Women's Day, where we had people on the panel. Ashwini was there in the panel. Vatsala was the moderator for that. We had Jhansi, who was also there on the panel. Ram. And last year, in September, we also had the National Convention. So the National Convention happens in one of the places where ASEI presence is there. So last year, it was in Michigan, and it was a really grand event. So this is something which we had in February. Anjali Kota was the speaker. This was a virtual event. University Connect, which Ritu was heading. So this was in March. Yeah, and this is from the International Women's Day in March. And then we, in the science fair, we had the ASEI board members, as judges in the, and Sridhar was heading that one. And ASEI awarded the student projects. And today we are here to hear Professor Janice. Before we move on to the speech, I just wanted, like, if you want to be an ASEI member, I thought like Ram would be the best person to talk about it. What you get, if you are an ASEI member.
Okay, good evening, everybody. All right, I'll be brief because I know we're waiting for the professor to learn about climate change, but I think most of you are either members or have been in the past. But as Lalita very ably mentioned, we have multiple pillars. We basically try to start young, middle school, and that's what the science fairs are about. Sridhar handles that in the team. So we go to schools, we encourage kids to get into STEM, do science fairs, do projects. And then what we do is take them once they go through middle school, we get them in college through University Connect. So Ritu just opened a chapter at Michigan Dearborn. We're trying to work with Lawrence Tech as well. We have some kids at U of M Ann Arbor trying to start a chapter. There's chapters around the country. So we get them into, college, and then after that, once you get working, we do Mentor Connect. So we do one-on-one mentoring, group mentoring, and we try to pair people with 2 or 3 levels above. So if you're a C-suite, you get paired with a president or a CEO. If you're just starting your career, you'll get paired with somebody with 5 to 10 years experience. And then we continue along as you go and get to my age, you become a mentor. So, the cycle continues for the kids who get in early. We do these science fairs, and then they all get to send their projects in annually to our annual convention, which is around the country. So just a great opportunity for everybody to get involved with science, and that's what we encourage doing. So lots of memberships, great networking, looking for jobs, looking for first job, looking for connections, great way to get in, right? And it says ASEI, but we're open to all, right? So just make sure. So thank you. With that, I'm sure you're going to introduce the professor.
Yeah, and Ravi is going to introduce.
Thank you.
Good evening, everyone. I'm Ravi, and I have the privilege to introduce Professor Means. And thanks for coming here and educating us on the climate. She's a veteran in the field of solar energy and sustainability. She's got more than 50 years. She's got a long bio. I'll try to be brief, which is she's served in the boards of Great Lakes Renewable Energy Association, the Detroit ASHRAE chapter, and the Michigan Solar Energy chapter, and the Michigan Interfaith Power and Light. She's also Emeritus Prof at Lawrence Tech, and she's also the past chair of ASHRAE's technical committee. She's written books that's published in the 2021 ASHRAE Fundamental Handbook and ASHRAE's 2019 Energy Guideline for Historic Buildings. She's also co-editor of multiple editions in ASHRAE Green Guide Design and Construction and Operation of Sustainable Buildings. Thank you, Janice. And she's also received multiple awards, and she's been an ASHRAE Fellow and ESD Fellow, and she's got an international award for outstanding service and achievement in teaching from the ESD and also from ASHRAE. And she's also an outstanding engineer, a PE and Gold Award winner from the ESD side as well. So without further ado, thank you, Janice.
Thank you. Yeah. To be able to share my knowledge with you, because I think it's so important that everyone know about climate change. And there's so many myths out there. So we're going to destroy the myths, and you're going to learn about what's the reality, okay? To get started. Way. Oh, I get rid of that screen. Okay. I start with some learning objectives. As you know, I have been a professor, so we have to have learning objectives. But at the end of this presentation, you should be able to describe how current global climate change differs from natural cycles, because there is a difference. You'll be able to contrast both weather events and climate change, because those are different also. Explain how volcanic eruptions can they actually affect weather, not so much climate change, you'll be surprised. And list at least 4 changes the world has experienced today, because the whole world is experiencing climate change. And this is it, which really convinced me. You're going to be able to talk about isotopes of carbon. I know you're all engineers, or for the most part engineers, so you know what isotopes are, but I'll explain it anyway, because I'm in the habit of doing that. And you're going to find out how we can tell which carbon up there, which isotopes are actually from fossil fuels. And then you're going to be able to give an example of mitigation, adaptation, and providing resilience. And before I really get started, I'd like to let you know that I have all my slides numbered. So please hold your question, write down the number in your question so you can ask me at the end. And when you do, we're going to pass the microphone around so that everybody can hear you. So if you stop the microphone, they're not going to be able to hear you. Okay? Thank you. Oops. I would like to acknowledge the people that I've learned so much from this. And these are all people that have helped write or co-authors of writing the climate change chapter, which is chapter 36 in the FASHRAE Fundamental Handbook. I've learned so much from them. Most of them are PhDs. There are more people than I've listed here, but these are the main ones for it. So I want to acknowledge that, of them, okay? All right, we're going to start with an introduction. Climate change, myth or reality? We'll look at whether climate change is human caused or not. We're going to then talk about present and future climatic outcomes. And I take you from a world view all the way down to Michigan on that. And what can we do about it? Very briefly, we'll talk about mitigation, adaptation, and resilience. And then I'll have some concluding remarks. Okay, so let's get rolling. First of all, if we're going to talk about climate change, we need to have a definition, right? So this is the definition that the Intergovernmental Panel on Climate Change uses. It's a change in the state of climate that can be identified, notice this, by changes in the mean or the variability of its properties. And notice this part, persist for an extended period of time. This would be decades or longer. Are you good on? All right, so let's look at some signs for climate change. We have an increasing pattern of having abnormal high temperatures, as you can see here. In fact, starting about 1960 is when they start getting worse. So that's one thing to know. Others are the Arctic sea ice is melting. And even if you compare this last decade that we've had to the 1981 to the 2010 period, if you're comparing this to this, we're down 12.2%. And you can see in the pictures how it's melting. And they predict there'll be a time when there won't be no ice up there. There's also glaciers are shrinking and disappearing. I've experienced this myself. In 1975, I drove the Alcan Highway and stopped at the Columbia ice fields and saw them. And then in 1988, my late husband, Gary, was driving and he said, we're at the Columbia ice fields. And I said, no, we're not, because it looks so different to me. And then Joe and I, on our honeymoon, went there and it had changed so drastically. And this is a photo showing that. I also have been to the Mendenhall Glacier, which is in Alaska. And the visitor center is like down here. And I have to tell you, oh, by the way, the colors, the green is actually vegetation. The light blue is the actual ice field. And the dark blue is liquid water, okay? So you can see how it's melted back. And I was at the visitor center down here. They had a movie going, talking about the changes. But what really struck me is there was a blackboard where they were recording daily changes. So there, you know, it's happening. If you're not going to these areas, you may not see some of these changes. So also the global mean sea level is rising. Now, a few centimeters may not sound like a lot, but if you lived on an island that's just a foot above seawall, even looking at New York, for example, when we have surges and a lot of rain along with that, you're getting flooding. So the predictions are it's likely to rise from 1 to 6.6 feet. Now, the IPCC has different ways of looking at things. Like they look at it as if we're going along just as we are, if we're doing better than we are, you know, and they have the different ratings on it. They call them SSPs, but don't worry about that. So you can see that there's a range. I probably should also say that so far, all of the predictions have not been very accurate. And this is what it is. Things are happening more rapidly than ever predicted. Let me repeat that. Things are happening more rapidly than previously predicted. I think the IPCC has tried to be very conservative in making their statements to make sure that what they're saying is correct. Okay, and I thought that you might find this interesting, and maybe I can see if it'll go to it. Didn't. Okay. Shoot, sorry. Let me go back. Here we go. If I was going to bring this up because I could show you where Mumbai, for example, on here. This is, if you go to sealevel.nasa.gov, you can click on any place of those dots, and it will tell you what the current rise in sea level is, as well as what's projected. So I thought you might be interested in seeing that. I was going to bring it up, but it didn't. We better not lose the time. Okay. All right. So what about some of the weather that's been happening? We've had extreme weather. Every day you turn on your TV to see the news and you see some sort of extreme weather happening at somewhere, right? And by the way, Midwest, where we live, is actually part of one of the better ones. I did an article for the Tech Century. I'm creating, oops, that's the wrong one. The one that is the Midwest a refuge for climate change. Spoiler alert, there's no place that's a refuge for climate change, but Michigan and Wisconsin are pretty good for the United States, and you can go through and see why. So yeah, it's great news, isn't it? So we're having wildfires, and even if it's not in an area where you live, where we're having a wildfire, because we haven't had many we've had a few, but very minor ones in Michigan, we're still feeling the effect of them. Last summer, before going outside, I checked the air to see the particulates, the ozone level, and the temperature and the humidity. I never used to do that before, but now you have to. There's flooding taking place, even in Michigan. There's been flooding, and hurricanes are much worse because they're dumping more water. It's a much hotter earth, so the atmosphere is hotter. And you know yourself, when it takes heat to evaporate water, right? So more water is being evaporated into the air so that when a hurricane comes up, they're not more frequent because of climate change. They're just more severe because they're dumping more water. Okay, so why is it important to know? As I'm saying right now, it's real. Okay, 70% of the people, I just saw this and I haven't confirmed it, so take it as it is. 70% of the people in the United States believe that climate change is happening right now. And a lot of times we think that people don't, and I know you're almost afraid to say anything to anybody with the way things are. But anyway, it's an existential threat. It's happening right now. What you might be surprised to learn, and you'll see when I show you the figures on this, since 1960, the carbon dioxide has increased 100 times faster than in the last 800,000 years. 100 times faster. And you'll see the chart on that. Okay, so why am I lecturing on this? I think knowledge is important. I think if everybody understands what's happening, that they can share it, you can share it now that you have it, and I'll send a PDF of this so all of you can have a copy of it. And also, this is what our society, FASHRAE, American Society of Heating, Refrigerating, Air Conditioning Engineers, have said. This was in the last position document. I'm on the team that's rewriting it right now, but I'm going to make sure to keep this quote in it. Climate change is the most formidable environmental challenge ever faced by society. My voice is shaky because this scares me, and it should scare you too, okay? All right, so how do I get rid of this?
Can you drag it off?
Drag it off?
The more section.
Go to the, pardon me?
Hide the floating controls.
Thank you.
Yep.
And I should know that.
No.
Say, okay. All right. So now we're going to say, okay, we all agree that there is climate change, right? I've shown you all the things that are going on. So what was causing it? Is it anthropogenic? In other words, is it caused by humans? Or what? Is it you'll hear some saying it's caused by natural forces. We're just in, it's caused by solar activity, right? Well, let's look at the data. And on this chart, starting in 1880, going to 2020, on the left side, and don't worry about the numbers, but this is irradiation from the sun. On the right side is temperature in degrees centigrade. If you look to the left of 1960, it looks like there's some relationship, right? And I can see where people would have thought that. But since 1960, the actual irradiation has gone down. And what's happened to the temperature? It's accelerated up, okay? So is it caused by volcanoes? You might have heard, how many have heard that it's caused by volcanoes? Anybody? No? Okay. All right. So what happens when we have a volcano? Now, there are different kinds of eruptions. There's some that don't put a lot of product or particulates into the air. Some of them just have the lava flow. The ones putting particulates in the air, what goes in there? We have sulfur dioxide, we have carbon dioxide, we have hydrogen fluoride, and hydrofluoric acid. The hydrofluoric acid comes down as acid rain, okay? The sulfur dioxide turns into sulfuric acid when it reacts chemically with the hydrogen in the air. In any case, all these cause particulates which block the sun coming in. And if we look at the amount of CO2 that comes out of volcanoes at the present time, it's very small. It's less than 1% of that released by human activities. But you'll say, well, wait a minute, millions of years ago, there were all these volcanoes, and that caused the excess CO2 and the excess heat. That's true. But we don't have all these volcanoes going off now. So it is different. So let's look some more. What about submarine or underwater volcanoes? And there's been some hullabaloo about this. So part of it is because there have been more underwater submarine volcanoes discovered than what they thought were there. But there's no record showing that they're erupting any more frequently than they were before, okay? And also part of that is that the Earth is experiencing relatively high sea levels and lower orbital eccentricity, okay? And your orbits are more round of the Earth going around the sun. So we're not getting it. And if we look at temperatures, if you measure the temperatures close to the surface of the water where it interfaces the air and compare it to deeper waters, it's hotter at the top than it is at the bottom. So this doesn't really make sense. But what about the unique Hunga Tonga Hunga Halapai, I dare you to say that 3 times, which occurred in January of 22. Did anyone remember hearing about this? It was quite extraordinary. It put 10 to 15% more water in the air than existed. And I say the air, it was up in the troposphere, not the troposphere, the stratosphere, troposphere is the area. It varies in height, maybe about 10 miles from the Earth, where you change over to the troposphere. But that's where all our weather happens, okay? Troposphere is much higher. So shortly after that, this is from 23, they said the shortwave heating and long wave cooling by the aerosols appear to roughly cancel. But what it did have an impact on was our ozone layer, okay? The ozone hole. And remember, we stopped using chlorofluorocarbons as refrigerants, yeah, okay? And we were very successful in closing that hole up a bit. Well, this actually caused the hole to open a bit, okay? And let me address that. I forgot to address the water, so let's address that. What happens with water in the air? Well, water doesn't stay in the atmosphere very long. It goes through cycles, right? So it dissipates. It doesn't make that big a difference. All right, so let's look at volcanoes. I had heard from my PhDs on the committee that volcanoes don't do much, because I, like most people, thought that volcanoes probably do a lot. And they said, no, it provides cooling. So I thought, okay, I looked at this chart or graph from 1880 to 2020, which lists the temperature anomalies going up, and it's been averaged here. You can see in the black. You're going to see this chart a couple of times. And what I did is I plotted the volcanoes that occurred, and the first one's Krakatoa, the South Pacific, 1883. Oh, wow. Temperature went down, but it doesn't stay. It's a temporary thing. So then the Navarupal, I'll probably murder these the pronunciation. I have to tell you, I have trouble sometimes pronouncing words. My father was born in Paris, Tennessee. And my mother was from Boston. And when I was a small child learning my numbers, it took me a long time to figure out what the difference between 40 and 40 was. So anyway, that's my excuse, and I'm sticking to it. So the Navarupal, it was in Alaska in 1912, was the largest volcanic eruption in the 20th century. And look at how far down it pulled the average temperature, okay? So moving along, if we look from 1943 to 1952, the Periaton in Mexico, it lasted over a time, and you can see it kind of flatten things out. It pulled it down, we're flattening out. Then we go on to the Kilauea, 1969 to 74 again. You know, we pulling it down. Mount St. Helens, and I can see this. I couldn't say this to my students when I gave it to them. How many remember Mount St. Helens? Yeah, there was a lot of stuff that went into the air, right? Mount St. Helens, 1980. Mount Pinatubo in the Philippines in 1991. And then this one, 2010, Jalajokul in Iceland. I've been to Iceland, and I know it's hard to pronounce a lot of their words. There is one nice thing there's a lot of nice things there, but if you're in a shop or something and they say goodbye, they always say, bless, bless, which I think is very lovely. Okay. Any case, when this one went off, I was giving a talk for Klima 10, which is a climate-related presentation in Turkey. And I caught the last plane back before they were going to stop flying, because there are a lot of problems with the air because of the volcanic eruption. So what can you say now about volcanoes? Do they cause climate change? They actually cause a few years of cooler weather. So we can thank our volcanic friends for helping us keep the temperature as high as it might be. All right, let's talk about, you often hear the people saying, well, this is a natural cycle, right? You've heard that before. So is it? So let's look at some natural cycles. There's something called the Balanovich cycle, and it relates to the eccentricity of the orbit that the Earth makes around the sun, as well as the fact that our axis wobbles a bit, okay? And we can affect, yeah, thank you. He's showing how it wobbles. We know that the ice ages relate to this. How do we know 800,000 years? Does anybody know how they found this out? What the records are? Core samples, not the Peace Corps, no. Core samples taken in Antarctica. There's a wonderful film I saw about the fellow that did this. They kept having to build stronger and stronger drills to be able to get down. And they had to go, I forget how many 100 feet they had to drill down to get 800,000 years ago. But they can actually look at the air that was captured in air bubbles. And from that, they can tell, you know, how much CO2 was in there. They can tell the temperature. They can tell a lot about what happened then. So if you look at this, you can see we've had 1, 2, 3, 4, 5, 6, 7, 8 ice ages. Okay. And by the way, the dark blue on this is the CO2 levels. Oh my goodness. CO2 relates directly to that. And the blue, light blue, is temperature. Oh my goodness. Temperature and CO2 are related, okay? This is another chart. This is on global mean sea level, and it goes back 771,000 years, which is pretty close to 800,000 years. But I think that you can see that if you put that on top of this, it would pretty well track, right? Okay, so these are the natural things going on. And you're gonna see that chart on the left a little bit later when we'll talk about what's happening now and what's been happening in the last couple of 100 years. All right, so let's talk about carbon dioxide levels. This, and first I'll say, I looked this up. The latest I could find was for 2 days ago, and it's 427.21 parts per million carbon dioxide. Now, if you look today, that number will be different. It goes up and down. As you can see on this chart, it goes up, it varies, okay? But it also varies on where you take the reading and what time of year it is. Most of our readings, like these, come from Mauna Loa, Hawaii. Mauna Loa is in north latitude. It's only 20 degrees north latitude, but it's still north latitude. If you compare that to the Amazon rainforest, which extends between 3 and 12 degrees southern latitude, south latitude, you find out why this goes up and down. So let's think about this. In starting January, it's moving up, the CO2 level. Right about the middle of the year, it starts moving down. Any ideas why? Well, when it's our summer, it's winter there, right? And vice versa. So when it's our winter and it's summer there, the Amazon absorbs much more of the CO2. Okay, so that's why you get it going up and down like that. So let's look at CO2 levels for the last 800 years. This is basically the chart you saw before where I pointed out all of the ice ages. Only now I'm showing you what's happening today. Crazy. If we're doing a natural cycle, what do you think should be happening today? Should be going down. If you go to Cranbrook Institute of Science, in fact, they've talked about taking this exhibit down, you'll see an exhibit of Detroit with ice coming in and destroying it. Because what we knew from here, we thought that we were going to be cooling, and we should be in a cooling period, but we're not. So let's look at the CO2 levels. All of this 800,000 years, the CO2 level never exceeded 300 parts per million. In fact, it only exceeded that one time. All the rest of the times it was under 280 parts per million. Okay. In 1911, it was the first time that we hit 300 parts per million. Okay. On May 9th of 2013, 10 years ago, they hit 400 parts, or excuse me, yeah, 400 parts per million. I'm talking about exceeding what it had been. This is most likely in the last 3 million years. Okay, now million and million years ago, it was very hot. Remember, I talked about all those volcanoes. But we're not going back that far. We're looking at what we can actually read from the data from the ice age. So this is, if you look from the mid-19th century to today, it's 10 times faster. But as I mentioned, from 1960 to today, it's 100 times faster. Now, and you can see, you can't read it because it's going straight up, right? Virtually is straight up. But even if we stretch it out, it's still going up at pretty high rate. So this is a chart you saw before on temperature, again, going from 1880 to 2020, and then we have degrees centigrade on it. And since 1880, as I mentioned, it's 10 times faster than the average. And these numbers here, 2 degrees Fahrenheit, which is 1.1 degrees centigrade, is what was listed in the most recent IPCC report. Okay. If you look on the internet today, it is over 2 degrees. It's over 1.5 degrees centigrade. Now, in the last year, it has exceeded and touched, it's gone to 1.5, but they look at it for the whole year. So we aren't there yet. But does anybody remember this is the number they were trying to keep us under, 1.5 degrees. And we're already, pushing that limit. We're ready to crack through that ceiling. So the fastest warming, as I mentioned before, occurred in this period from 1960 to 2000, and you can see the difference. It's still going up, but it's relatively flat. But then you look here, and it's really going up very quickly. The 10 warmest years have occurred since 2013, the last 10 years. In fact, trying to remember, since I think don't hold me to this, for the last several months, since this summer, every month has been hotter than the year before. March, it didn't have that much a difference. In fact, it's within the range of error, okay, but it's still showing it higher than it was. 2023, I don't have to tell you this, it was the hottest year ever recorded since we're keeping records. And if we can go by what we do from the ice cores, it's ever from 800 years ago. So I wanted to share these because you might want to go here. This is called climatelevels.org. And what's neat is you could click anywhere along here and it'll give you a number. So for April 21st, CO2 parts per million were 427.29 parts per million, okay? Global temperature, 1.39 C on March 24th, or March of 24, and September of 23, sea level was up 24.8 centimeters. And again, centimeters might not sound like a lot, but it can make a big difference. So right now, 1.39 is 2.5 degrees. And it's 28.8 centimeters is 9.77 inches. Okay. All right. So let's look at what causes the Earth to heat up. It means that you have more heat coming in than you're putting out, right? You're all engineers. You take a control volume. If you have more coming in than going out, you're going to heat up. So why do they call it the greenhouse gases? Because the greenhouse gases act just like a greenhouse glazing, okay? Greenhouse glazing lets the short wave radiation go through. Once it heats up and turns into infrared, it bounces it back. Okay, does it totally bounce it back? No, but it does cause heating. In the mid-1800s, and ladies in the audience, I want you to hear this. How many have heard of Eunice Newton Foote? She actually did experimentation in 1850s and discovered that CO2 and moisture in air, and she tried them separately, would cause warming, would cause the atmosphere to heat up. Dalton got credit for it. Dalton was famous Irish, well represented, should I say financially, you know, from Ireland, and he got credit for it until 2010. This fellow was reading, he liked to read journals, and he read this and said, oh my goodness, she discovered it. So she's just getting credit for it now. So remember her name, Eunice Newton Foote. In fact, I did an article on her for the FASHRAE journal, which I don't know you'd have access to, but if anybody wants a copy, send me an email and I'll be glad to share it with you. Okay, so let's talk about greenhouse gases. What are greenhouse gases? And they happen to be, in the order of importance, water vapor, if you will, carbon dioxide, methane, nitrous oxide, ozone, and something called F gases, which are fluorinated gases, okay? And you say, well, water, I've never heard that water causes it. It does. It's the most influential, but scientists don't count it because the water changes and goes through cycles so quickly. And because the the atmosphere is warming up, more moisture is coming into it. So it's more looked at as a feedback rather than an actual cause. Then we have, and by the way, I've listed some of these ways that greenhouse is caused: changes in landscape, the burning of forest, agriculture, a little bit from volcanoes here, as you know, not a lot, eating beef and sheep, because they're ruminators and they give a lot of methane off, our transportation, our industry, our homes, even forest fires, moisture in the air, as I mentioned. And these are the F gases, hydrofluorocarbons, PFCs, which you've probably heard of, and the sulfur fluoride or sulfur hexafluoride, which I didn't know what that was. I had to look it up. It's a gas that's used a lot in electrical equipment to cool. Okay, they're escaping. They're not supposed to escape, but they do. And so, and they actually only contribute like 2%, we think. They think it might be a little bit more now. So then we have reflection and shading, which cause global cooling. So if these aren't equal, what do we get? We get radiative imbalance, right? And if the global heating is higher than the shading, of course, we get heating up. So here's the question. Is it caused by people? Okay. Do we have evidence to show that this is caused by people? Let's look at the evidence. Is it myth or reality? Almost seems like that show. What was it? Is that myth or reality? We're going to find out here. Okay. So let's look at this chart. It's kind of a busy chart. So let me walk you through it. The blue on this are the natural drivers, okay? The red are human drivers, and the black actually shows what's observed, and the gold shows everything together. Look at the gold and what's observed and what's predicted is pretty much right on, right? Okay, so, okay, let's talk about those carbon isotopes. Okay, you know, carbon has an atomic weight of about 12, which means what? It has 6 protons and 6 neutrons in its nucleus, right? If it has an extra neutron, we call it carbon-13. If it has 2 extras, we call it carbon-14. Wow, what do we use carbon-14 for? We use that for dating. not people, but. Okay, we use that for dating. Carbon, why can we use that for dating? Because it's radioactive, right? So the carbon goes away. Our fossil fuels have been around a long time, right? Do you think they have much C14, carbon 14 in them? Zero. They have a little bit of carbon 13. So let's look what's happening here. Okay, as I just mentioned, if it's the carbon from fossil fuels, it's going to have a very low incidence of carbon 13 and no carbon 14. So let's look at the CO2 levels. Now we've already talked about how it's increased 40% higher in 2019 than in the 19th century, 50% higher today than in the 19th century. But the fraction of carbon isotopes 13 and 14 has significantly gone down. What does that tell you about what's causing the increase in carbon dioxide? The fossil fuels. When I read that, I thought, oh my goodness, that really says it, doesn't it? Okay. So the IPCC, I mentioned before, they've been very conservative and very, very careful with what they've said. And in both 21 and in 23, they said, quote unquote, it is unequivocal that human influence warmed the atmosphere, ocean, and land. And if we look back, when they started in 1990, the first report, they didn't say that mankind caused, or humankind caused anything. 1995, oh, we got some evidence here. Look at it now. And then that's 2013, but now it's fully caused primarily by humans. So is today's climate change anthropogenic?
Yes.
Yes. Okay. Very good. These, and I wish I could find a more complete list because I know FASHRAE isn't on this list and I know there are other ones, but this is a list of worldwide scientific societies that hold the position that climate change has been caused by human action. If you look back through the records of Exxon, they knew this decades ago. Their scientists predicted that and they hid that information. And they're still trying to fool us and thinking, oh, it's not a big deal. Anyway, sorry. What happened? Did I lose? Oh, it went to the ketchup. All right, so now, is everybody convinced now? Yeah. I think I've got a pretty good argument going, huh? All right, so now you know what to say when someone says, oh, it's caused by volcanoes. What are you going to say? No, volcanoes cause cooling. Okay, and you've got the other. Pardon me? Okay, so let's talk about some present and potential future climatic outcomes, okay? Climate zones are on the move. Okay, this is of the world. You'll see one of North America in a minute. All these little white dots, which are hard to see, are actually showing where climate zones have moved up. By the way, the climate zones are color-coded here. Say for India, a lot of it is in a new zone called 0. We didn't used to have 0. They started with 1 and went up. But temperatures have been going so high, they had to add a new climate zone. So a new O, okay? In the United States, or excuse me, in North America, they've moved up about 100 miles north. And I don't know about you, I grew up in Waterford Township, and not that far from here. I never saw an egret. I see them all the time now. Because they've been moving north. Can plants move as easily as animals? No, they can't. So our vegetation is changing, and I'll get more, I'm getting a little off topic here. But anyway, so global temperatures have increased over 2 degrees Fahrenheit since the 19th century. And I want to thank my good buddy, Michael Roth, who puts these together. He always lets me take them and put them copies. We have them also in our chapter there. So global extreme events are more frequent. We had heat waves. I know I won't even go into it. Since in 2023, 2023. There were heat waves throughout the world. What I found really is astounding that the ocean near Florida had recorded water temperatures exceeding 100 degrees. I thought this is the ocean, you know, that last summer. And even a couple of years ago, I remember that the seafood were dying. Boy, that tells you I like seafood, doesn't it? Okay, the sea animals in Oregon and Washington, they were dying because the ocean was so hot on there. Extreme rainfall, and again, I've listed the places, I'll let you read it. Drought in many areas. And by the way, a lot of these areas that had drought are now having extreme rain and flooding. Dubai, for example, is flooding. And Jim, I know you've been to Dubai. What's Dubai? It's a desert, right? Yeah, it's a desert. They're having flooding there now.
It was because of something else. It was because of manipulated.
Manipulated. Oh, we won't go there yet. There's a lot. Record deadly deadly wildfires. And again, as I mentioned earlier, we've been experiencing the effects of that. It's expensive. Okay, it's expensive. I know that one of the arguments that people make is it's too expensive to do anything about climate change. I'm saying it's too expensive not to. Okay, and I've got some numbers on here. Just in Hurricane Ian, for example, in September of 22 was 113 billion with a B dollars. And they probably don't have all of that added in now. China floods greater than 12 billion. China drought, that was the two, greater than 8 billion. European drought, more than $20 billion. Southwest drought in the United States, about 22 billion. Okay, so it's just expensive. So what are the consequences of this? We get food insecurity. It damages people's health. Biodiversity is seriously threatened. I remember plants can't move, and some animals can. In fact, part of our health issues is that insects that normally weren't in, say, certain areas are now moving north. Okay, and we're having issues. Most vulnerable are who? The young, the elderly, the poor, okay? Especially minorities and indigenous populations. Okay, the people basically that didn't cause the problem are the ones that are the worst hit. I'm gonna cry, sorry. I get emotional about this. Poor nations also are getting the brunt of it. They get all our plastic too, by the way, seems, unfortunately. So this is anybody who wants to look at other places to find out how things are changing. I've got 3 sources here, one for Canada, one for Australia, and one for the European Union. And there are probably others. I've asked people, if you know of others, let me know, because I want to look. FASHRAE, even though it's American Society, it's an international organization. And so I like to do things internationally. So remember I showed the map of the world? This is the United States. And again, every place you see a white dot, it means that the climate zone has moved. The only place they actually have gone down is down here, which is interesting. Okay. Temperature changes. Oh my goodness. Look at this map here. And I'm going to focus in on Michigan. Where are the reddest areas? Those are the hottest areas. In fact, the extreme hot is more than 4 degrees. What did we say that the world is at? About 2? Okay. Look at Michigan. And I made a copy of that up here so you could see it better. Northwestern Michigan over here is heating up much faster. It looks to me like greater than 3. It might even be 3.5, 3, definitely greater than 3. Okay, Michigan is heating up faster than some of the other places. And I thought this was interesting. Look what areas are getting cooler. Who would have known? The hot areas, we think of it being hot in Louisiana and Alabama and Mississippi, right? But those areas are actually getting cooler, okay? Isn't it crazy? There's the author of this book, Catherine Hayhoe, who's wonderful, is so wonderful. She always says that climate change doesn't cause a lot of this weather. It just weirder, how did she say it? It makes it weirder, okay? Weirder weather. That's hard to say, weirder weather. Try that 3 times too. Okay. So here are the mid-century projections that they're, saying, and this one, if you look again, parts of Michigan here, we're going to increase to about 5 degrees hotter. I can't imagine what that's going to be like, okay? And that's for mid-century. I won't be here. Some of you might be. I won't be. Okay, let's look at precipitation. Michigan is also becoming much more humid. Okay. In fact, all the Midwest seems to be becoming more humid as opposed to some of the Western places where they're continuing to have drought. We're getting 20 to 30% more precipitation. What happens when we have high humidity and heat? Source, our bodies, if you look at charts on how our bodies expel heat, when it's 100 degrees and high humidity, your body can't sweat, so it cannot lose heat. So eventually you die. Seriously, okay? So it's a serious thing that we're getting high humidity. All right, these are precipitation projections for mid-century. Again, parts of Michigan, these darker colors, are they're going to have maybe 4 inches more precipitation. I'm assuming that this is an annual. And at mid-century, the number of days that we have heavy precipitation, again, up here in the northern part of Michigan, 1.5 days more. That may not sound like a lot, but it can be. So what happens when we have increased precipitation, increased humidity? We get sewage overflows, okay? Primarily because we're not keeping the stormwater on our site. There are a lot of ways to do that. You can go over to Lawrence Tech and see many ways. Just walk around campus, you'll see signs. There's bioswale, there's rain gardens, all sorts of things. It's called LIP, L-I-P, low impact design, keeping the water on. So because when it rains so hard, the stormwater can't keep up with it, and that's where you get the sewage getting mixed with it. It's going into our waterways, the Great Lakes. 90% of the fresh water in North America is in the Great Lakes. 20% of the world's fresh water is in the Great Lakes. We're very fortunate to live where we do. We have increasing erosion and algal plumes, flooding. What does that do? It disrupts so much. I mean, it damages things, but it also disrupts transportation networks, rivers, erodes. It negatively affects agriculture. It changes what we're able to grow. It's increasing human health issues. But the good news is we have a decrease in threats for wildfires in Michigan. I mean, no, that is a good thing. I shouldn't make light of it because it is a good thing. Okay. So what else does it have? Lake surface temperatures increase. We're having greater stratification, earlier stratification. Our summer lake evaporation rates is hotter, more water is going up. And what happens when the water goes up? It's going to come down sometimes. We have these storms. And that's one of the things, if you read the article about this being a great area to be in, is we still will have sudden and severe storms. That's our biggest threat, okay? Beach health will decline. And you already know the last few years, there are areas you couldn't go swimming they've been closed. Agriculture is effective. It can be positive or negative depending on it, on the crop. Lake cover and decline extends commercial navigation season. That's another positive. They're more likely to be able to transport materials. Air and water decline, ground level ozone concentrations increase. Residential health is going to worsen with the invasive species, which I mentioned before, insect pest and plant disease. And if you just look at the crazy weather, look at the crazy weather we've had in the last 2 weeks. What was the hottest temperature? Remember, didn't it get to 80? 80? And what's the coldest last night? You know, we were looking on the way here, seeing how many plants had died. Unfortunately, it looked pretty good. So a lot of people did it early. So what about extreme weather? The United States, actually NOAA, National Centers for Environmental Information, keeps track of, get this, only the $1 billion events. So if an extreme event costs at least $1 billion, they record it. If it's less than that, it's not recorded. Okay, so there are a lot more in here. There have been 376 of these events in the United States since they first started recording them. Over half of them were in Texas. Where are a lot of people moving to? It's crazy. But anyway, how many were in Michigan? 52. Deaths from these events. People died during these events. Over 16,000 people. Fortunately, only one person in Michigan. Cumulative cost in billions of dollars, $2,661 billion. For us, it's between 10 and 20 million. Still a lot of money, right? Average events per year since 1980, 8.5, 1.2 for Michigan. But if we look just from 2019 to 2023, there were 20.4 on average, and Michigan had 3 on average. So the number of these extreme events are increasing, and so are the costs, okay? And it all is related to climate change. All right, this is a very difficult graph to look at. So let me walk you through this. This is for Michigan as the $1 billion weather and climate disasters. Along the x-axis, we start with 1980, because that is when they started recording these, and it goes to 2023. On the left side is the number of incidences. So for example, right here, we have 2 incidences in 1982, okay, for example. And on the right, we have the cost in billions of dollars. Now, the cost are the pointy parts, okay? And this is the average cost, goes all the way along there and up. And let's look at how the events are counted. There were 52 total events. Remember, I said that before, for Michigan. 36 were due to severe storms. Now that's all the green. So there was 1 this year, 1 that year, 2 here, 1, 2, 3, 4 in 2003, and so forth. The ones that have the square top. The next are 6 due to winter storms, and that is in the purple, okay? And you can see that there are a few along there. There, and you can count them, you know, count the numbers that relate to. There are 4 due to flooding, and that is the darker blue. And 1 due to crop freeze, and there's only 1 that I could find, and that was here in 1982, 83, in between. Yeah, 1982, between 82 and 83, well, the winter. Okay. So that's how you read it. Does it look like they're increasing? Yep. Going, and the cost again is increasing. So climate change is very costly for us in many ways. Now, as I mentioned before, this is what we have to watch for, the severe storms. And we don't have time to get into, I have another presentation, by the way. I could get into what needs to be done to buildings to make them more resilient for that. But for Michigan, we have to do something to our buildings to make them safer when we have storms, okay? All right, so let's talk about mitigation, adaptation, and resilience, and we're getting toward the end. I don't know how I'm doing on time. Okay, how can we handle climate change? Well, we can mitigate it. What's that mean? Basically, you can think of avoiding the unmanageable. So you want to decrease or eliminate, hopefully eliminate CO2. We do this by decarbonizing, using renewable energy, and possibly looking at carbon sequestration, where they can take the carbon out of the air. And there are a whole host of things I could talk about on that, but I'm not going to get into that right now. Adaptation is, you can think of it as managing the unavoidable. And this is where we want to use smart design and operational changes in buildings and the way we do things ourselves personally. And a lot of professional societies are addressing this now, and many publications out on it. And then resilience. Resilience. We want to maintain operations while managing a disturbance, okay? And that means we need to provide refuge areas. We provide refuge areas now, like if there's a fire, right? You can see the sign on the door. There should be some in here, and I don't see them. So it would tell you where to go in case of a tornado, for example. But in this case, it would be for whatever it happens to be the event. We want to be able to protect people. We want to protect buildings and equipment. Okay, so is it it's a reality? It's not a myth. And I think I've convinced you, right? That climate change is here. It is human cost. Climate change it's increasing. The CO2 is increasing an order of magnitude faster than the last 20,000 years, and 2 orders of magnitude in the faster since 1960. It's caused by human activities since the mid-20th century when we started using fossil fuels in excess. We have to look at our strategies to mitigate, adapt to the changing climate, and provide for resilience if we're going to survive. The ASHRAE Fundamental Handbook, which, by the way, you can go over to Lawrence Tech and you can see this chapter. This, you'll notice if you do, this one's a lot wider than what they have at Lawrence Tech because there was a snafu and they left some things out. None of our names appeared in front. They do on this one for credit, but you can still read the chapter. ASHRAE is committed to making humanity safer in buildings. So not addressing climate change, where people are dying from it. We're getting extinctions of species. That goes for flora and fauna. It's greater monetary expense, and I think it costs more to not do something than it does to do something. And the poor people, the indigenous, the very young, the very old are the ones that are suffering the most from it. So I can't let you go without giving you some good news, right? Other than we don't have forest fires in Michigan to speak of. Okay, more and more, we're seeing more awareness on this. I want each one of you to make a commitment to talk to your friends, your relatives about this. You have some data now. You have some things that you can concretely say. If someone says, oh, it's all a natural cycle, but you know what to say now. Renewable energy, solar energy is cheap. It's cheaper to build a solar plant today than to build a coal plant. That's amazing. So solar is so cheap. And then now with the IRA passed, you can put it on your roofs for so little money. It's just wonderful. There's a lot of research going on around right now for capturing and sequestering carbon dioxide. And some of it is being done by the oil and gas companies, and some of it's being done so that they can push more carbon back in to get more product out. That's not what I think needs to be done, okay? But there are other ways being developed. Right now, it's very expensive. Just to give you a little taste for it, There's one process where they actually take carbon dioxide from the air, it could be from a building, okay? And they take that carbon dioxide and they convert it to solid carbon and hydrogen. And you can sell the carbon, you can sell the hydrogen. In fact, hydrogen is probably going to be used more and more for transportation. Okay, that's just one. We can move to safer locations, rebuilding in an area that's going to flood every year or it used to be every 100 years you might get a flood. Now it's every 10 years or every 2 years, whatever. We need to make our buildings more resilient. We can use less energy. Each one of us can do that, okay? And if we act now, things might not get better, but they won't get worse. And I don't know how much longer I can say that last line, okay? We're way behind on what we need to do, okay? So Catherine Hayhoe's the one who wrote this book, which is actually a really good book. It talks about how to talk to people about climate change. And she basically says, find some common ground. You both have children, talk about your children and what we want. We want good things for children, right? For children. So now it's important to do something about climate change. This is what she says. It gives us cleaner air and water, protection from disasters, helps us grow more crops, provides more affordable energy, reduces gender, racial, and socioeconomic inequality, makes our city safer, and gives us a more stable world. That's what she says. And I have to share one more thing. And this was actually handed out in a climate talk. And it's really from Weather Chris. Do you remember his last name, Joe? Pardon me? Chris Edwards, that's right. I knew that and I couldn't remember. I'm so bad on names. Chris Edwards, he said 10 things you can do, and I think he got most of these from drawdown.org. Says talk to people about climate change. You have the information now. Plant trees or preserve existing ones. Oak, beech, and maple have the best. Fly less. Purchase carbon allowances. Non-stop flights release less carbon. Eat less meat and dairy. Like I said, talking to an Indian. And I'm going to have to talk to you much about eating less meat. Okay. Plant-based foods produce much lower emissions. Leave the car at home more. That is awfully hard to do in Michigan, I know. But combine, try to carpool, run all your errands at the same time. Reduce your energy consumption. LED lights have made a world of difference, and it makes it much less expensive. And you have to use less air conditioning when you're using the LED lights, because the old incandescent lights and even the CFLs gave off a lot of heat. Okay, invest responsibly, support solar and wind energy, cut consumption and waste. And by the way, I just recently found out about 4% of the methane going up is from our garbage dumps. And we're accepting garbage from Canada and all sorts of places because we charge so little. Another break of mine. Join local groups. You can Google Michigan groups tackle climate change. Vote with climate in mind. Seek candidates' climate views. And there's so much more. And I'm sure that you can think of other things that you should be doing. And I thank you for your attention. I'm sorry I've run over. I get very emotional about this, and sometimes I run off at the mouth a bit. So thank you. Okay, if you have questions, I'm going to ask you to